Ladies and gentlemen, my name is Nursultan Kabylkas, and in this presentation, we'll be talking about effective processor verification with Logic Fuzzer Enhanced Co-Simulation. Here's the quick agenda. This talk is organized in the problem-solution format. So I will start by giving a quick background on the verification. I will present some challenges in today's practices and then propose the tools that address those challenges. At the end, I will just quickly finalize with concluding remarks. Let's just jump right into it. I want to start with the real-world example when a single bug costed $17 billion to a company. I'm not going to name the company, but you should have heard about this situation. This story when a single bug in the battery management system allowed overheating of the battery and resulted in what you see on the screen. Well, obviously bugs cost money. But depending on when you find it, in which stage of the development you find it, they cost differently. I mean, the example that we talked about in the previous slide is an extreme case, right? That's when the bug ended up being in the customer end. And ideally, what we want to do is push all those bugs to the earlier stages, right? Try to find them, try to debug in the simulation phase. And no surprise, 50% of the time in a typical ASIC project is spent on the verification. The trend is that companies hire more design verification engineers. And on top of that, a design engineer actually spends 50% of her time on verifying the design. Now, the problem is, despite so much time and effort being spent on verification, bugs still end up in a silicon. And the data to back that up, less companies achieve first silicon success, meaning that they need more RISC-Vs to get to the working product. And 40%, about 40% of the bugs that cause the RISC-V are functional bugs that could have been easily, well, not easily, but could have been found in the simulation phase. Now, the term for those bugs is simulation-resistant superbugs. These bugs are complicated in nature, they require edge case scenarios, and as the name implies, simulation basically fails to achieve those buggy microarchitectural states. And the work that we are presenting in the paper are trying to address this kind of bugs. All right, now we know that simulation-resistant superbugs are an issue. Now we're going to switch gears and start talking about what we're actually proposing here. The upcoming slides are going to unfold two tools, Dromajo and Logic Fuzzer. What are they? In the paper, we are claiming that the combination of these two is better than the state-of-the-art verification infrastructure. And to be better, we had to at least start on the basis of the state-of-the-art. And Dromajo is nothing but a state-of-the-art verification tool for RISC-V processors. And Logic Fuzzer is an enhancement over state-of-the-art that allows finding more bugs and move them into the simulation verification phase. Okay, let's start with Dromajo. The best way to explain Dromajo, in my opinion, is by explaining the technique it implements. And the technique it implements is a concept of co-simulation. And that is on-the-fly comparison with the gold model. I mean, at this point, you might ask, what is a golden model? It is nothing but very high-level software abstraction of the processor. It's basically an emulator. It's in independent software. It's usually being developed in a different team, completely separate from the RTL designers. It's very simple, has no implementation details, it has no timing details. So things like cache misses, TLB misses, branch mispredictions, all those things being ignored by the gold model. And the changes to the architectural state happen basically on the instruction level granularity. Now, this couple of slides are animated slides that's going to help us understand the communication that happened between two independent softwares, right? So on one side, we have a test bench with the processor under test being instantiated as an object and its memory. So we compile that software into some executable. And on the other side, we have the golden model, our emulator, right? So after those two executables, after we have those two executables ready, we start the execution. And the y-axis, if you will, is the time. So we start the execution. At some point, we need to load the binaries that we're going to run. At that point, we need to synchronize the memories and the architectural state of the test bench and the golden model. And we have this communication channel that basically signals the golden model to get the data and synchronize the architectural state. We continue execution. At some point, we commit one instruction. We commit our first instruction. That's when we signal the golden model and tell golden model to commit instruction on its own side and perform the comparison. So green box basically indicates that with the comparison of the committed values are actually matching on both sides. And that's the success. We continue the execution. At some point, there might be the cases when the committed instruction have different values, and that's when this whole system, this kind of technique, basically tells us that something wrong is going on here, because architectural state has to be all the time. This architectural state of both sides has to be the same always, no matter what. At this point, we halt the simulation and we start investigation. We start debugging. Now, Dromadio is exactly what I've just explained. It is the state-of-the-art co-simulation verification infrastructure for 64-bit RISC-V processors. It implements RV64 GC model, and it designed specifically for co-simulation purposes. It is fast, it is lightweight. Now, very important bullet point right here. Dromadio is an open source. Dromadio is an open source software. It is hosted in the Chip Alliance GitHub repo. So if you were to design a RISC-V processor by any chance, go check it out. Make sure you integrate Dromadio into your processors. It's going to find a lot of bugs, I promise. Yeah, let's go into some more details of Dromadio. So the way we integrate Dromadio into our test bench infrastructure is by linking Dromadio as a shared library into the test bench, into the simulator. So RTL implementation right here, the box in the middle, communicates to Dromadio through DPI calls. So that communication channel that I explained in the animation are actual DPI calls in our case. And it is super simple to integrate, right? So it's just a matter of implementing 3 APIs, the matter of calling 3 APIs of Dromadio that will basically implement this communication between the model and the RTL implementation. Now the first one is the loading, is the synchronization of the memories, right? So when we load the binaries, we call Dromadio init, which initializes the memory of Dromadio by synchronizing it with the RTL. Another one, when we commit, we call Dromadio step API, which tells Dromadio to commit one instruction and perform the comparison. If comparison is successful, we continue. And there is also this Dromadio raise interrupt API, which I want to emphasize because not many tools actually support this. Even some commercial tools don't support that. So what it allows to do is supporting the asynchronous interrupts, right? So it can happen anytime, and we don't know when it's going to happen. And the problem, if you don't support that, the RTL implementation and the Dromadio and the golden model will start to diverge, right? Because the RTL will start executing the interrupt routine, but if the golden model doesn't support that, the execution flow will start to diverge. And Dromadio, basically, fortunately, it supports that, which means we can co-simulate even inside of the interrupt routines. And in the case when the mismatch happens, Dromadio halts the whole simulation and dumps specific information to the engineer so that he can start debugging. Now, Dromadio also addresses the issue of productivity with the checkpoints. I mean, this checkpoint is very novel, I think, in the verification space. So previously, we have seen this picture on the left, right? So that's when we load the actual binaries into the Dromadio instance and the memory. We can also implement Dromadio as depicted on the picture on the right. So we can run Dromadio standalone, meaning we can load some random instruction generated tests. We can put Linux, we can put unit tests inside of Dromadio and let it run for many cycles, and then dump the checkpoint. And the checkpoint is nothing but the snapshot of the architectural state, which we can then load into our simulator and start from that point. So I mean, the nice use case is basically boot Linux in Dromadio, run it for billions of cycles, and take the snapshot of the architectural state after billions of cycles and start the co-simulation from that point instead of waiting for billions of instructions when we were to load the binaries. Yeah, and what is the checkpoint? checkpoint is nothing but a generated bootron that brings any number of processors into the same architectural state. So it's basically a code that you execute, and after the execution of that code, on the same course, it's going to bring the many cores into the same architectural state. And obviously, we also have to dump the memory so that the loads and stores are not going to fail the co-simulation. So nice use case of the checkpoints that address the productivity is that we can boot Linux with Dromajo and let it run and basically dump many checkpoints at different points, right? So this might be 1 million instructions, this might be 500 million instructions, and this might be like 2 billion of instructions being executed in Linux. And then we can spawn all those checkpoints across many, many cores and execute the co-simulation in parallel. So this is a really nice feature. This really saves a lot of times of the design verification engineers as we can execute many co-simulations in parallel. All right, we're about to shift gears again. At this point, we should know how the processors are verified, and we should be familiar with the concept of co-simulation. We extensively talked about Dromajo, which is not really a novel part of our project, but it's an artifact, very useful tool for the RISC-V community. And right now, we're going to talk about Logic Fuzzer, which is actually a novel part, which is a methodology that we developed to address simulation-resistant superbugs. Now, the idea behind Logic Fuzzer is that we randomize microarchitectural state of the processor that does not affect the functionality. Meaning that we are able to expose variety of microarchitectural states that were not reached by running simplistic directed tests or even randomly generated tests. Now, there are many places in the processor where you can implement this methodology, and I'm going to explain 3 specific examples. We'll start with congestors. So what is a congestor? I want you to consider a simplistic FIFO, simplistic circuit, a FIFO and the combinational logic that feeds data into the FIFO and the full signal. Now, what we can do is break the full signal and insert a simplistic OR gate and randomly create the congestion, randomly create artificial back pressure. The semantics of this full signal should always be respected by the logic. And it is an implementation detail that never should be exposed and propagated to the architectural state. So if we create random variety of microarchitectural state by creating this back pressure, and it happens so that the architectural state gets changed, it means that the bug is present in the processor. Now we can apply the same concept to ready and busy signals. We ran a simplistic experiment on the Berkeley out-of-order machine, Boom, that consisted of 5 steps. We took 200 plus ISA tests and run it on the Boom. We divided the Boom, we measured the toggle coverage in different modules of the Boom, front-end, core, and memory access unit. And then we took one signal and inserted a congestor. So at the reorder buffer, we randomly toggled the ROB ready, meaning that we said that the ROB is not ready even if it was ready. And we run 200 exactly the same tests again. So what we found was that the toggle coverage actually increased. So in the front end, we had 12 additional activities. In the core module, we had 40 signals being activated. And in the memory access unit, 32 signals were activated. So this kind of, there are some issues with the toggle coverage as a metric that we discuss in the paper, but even this simplistic example proves that congestors are able to create additional microarchitectural states in the processor. Okay, another example is a table mutator. Table mutators allow non-architectural state memories to be mutated, right? A simplistic example is the branch predictor. So branch predictor should not affect the functionality. It's just a performance feature, right? So we can freely mutate the branch predictor tables and it should not affect the functionality. If it does, there is an issue with the processor. We can also randomize, randomly invalidate TLB or cache entries, right? That should not affect the functionality. Or we can randomly populate the data inside of the entries that has been already invalidated. That should not affect the functionality. Now, I want to go back and talk about the checkpoints again. Now, there was one issue that I didn't mention with the checkpoints, and that is that when we generate these checkpoints, we start all the simulation from the reset state. Now, table mutators can partially close this gap as we can randomly populate the microarchitectural tables that does not affect the functionality and create more microarchitectural states. Okay, example number 3. What else we can randomize? And that's the stressing the false path, stressing the mispredicted path. The idea is that no matter what we insert into the mispredicted path, it should not affect the functionality. Like this is another experiment that we ran on the CVA6 core. We inserted many random instructions into the mispredicted path. So orange line right here is showing how many unique instructions were inserted into the mispredicted path. And you see after running 200 tests, we see that not even 60% of the instructions in the RISC-V ISA were present in the mispredicted path. And it is important to test all the instructions in the ISA because some of the instructions in the mispredicted path can have side effects. And the blue line right here is showing how we inserted the random instruction to the mispredicted path. And you can see that when we reach 50 tests, we already covered all the 100% of the instructions in the mispredicted path. Another example is randomly generating the addresses from the branch target buffer. So that address should not affect the functionality of the processor, but sometimes, and like the results that we show in the paper, some of the cores actually had some effect on this actually had some effect on the architectural state of the processor. Now, when you're familiar with the tools and the methodology that we're proposing, the valid question to ask, how do we evaluate the tools? And the evaluation setup that we had is as follows. We took 3 open source cores, CVA6, Black Parrot, and Boom. We used Google's random instruction generator to spit out many instruction streams, and we also used simple ISA tests that were provided in the GitHub repo, in the RISC-V GitHub repo. Now, the metric that we used is a simple number, but it's a powerful number. It's a number of bugs that were exposed. So mere integration of Dromajo into the existing test bench infrastructures exposed 9 bugs. And the enhancement of Dromajo with Logic Fuzzer allowed manifestation of 4 more additional bugs by running the same test, exactly the same test. So we didn't put into effort in generating new tests or writing directed tests. It's exactly the same tests, and 4 more additional bugs were exposed. This is the complete list of the bugs that we exposed, and the detailed explanation of each bug is found in the paper. Yeah, it's time to conclude. So today we presented a challenge of finding a simulation-resistant bug. So much time and effort being spent on the verification, and still bugs end up in the silicon. We also sharing with community Dromadio, the tool, useful tool, powerful tool that can find many bugs in the implementation of the RISC-V processors. And we showed that Dromadio exposed 9 bugs in the open source course. And we also proposed Logic Fuzzer, which is a methodology that tries to push superbugs or additional bugs that were not exposed in the simulation into the simulation phase, which is kind of shown in this graph. I would also want to mention that we do not guarantee that the design is out of bugs. I mean, there is still research opportunity to find more bugs, to expose more bugs, and we also explain that in the conclusions and the future works in the paper. Yeah, thank you so much for listening. If you have any questions, please email me to the following email, and please attend our talk. Please attend the Q&A session that will happen on Wednesday, October 20th, session 6A at 11:30 a.m. Pacific time. Thank you very much.